Okay, this is the second part of the lecture on section 6.1. And the second type of line integral is the vector line integral. Right, the first was the scalar line integral. This is the vector line integral, or as I like to call it, the force work line integral. So given a curve C, okay, so this time the direction along C matters, represented by parametrization R of t equal to x, t, y, t, or in 3 dimensions, R of t equal to x, t, y, t, z, t for a less than or equal to t less than or equal to b. Again, think of t as a time parameter, so time in seconds, minutes, milliseconds, or whatever it might be. And, you've got this curve C along which that particle is moving forward along the curve in time, whichever way is forward. So now the direction is going to matter. So you've got some point moving through space along that curve. Given a vector field, if fxyz or fxy equal to pq, or fxyz equal to pqr is a vector field representing some kind of force, okay, then what we want to do is calculate the work done by that vector field. We want to define an integral that calculates the work done by F by force the field F along the movement of C. Right? Now, remember with vectors, right, how was work defined? So before doing this, okay, recall that if constant force F acts on an object moving from tip to tail, tail to head, on vector d, like that, then work, right? Work was force times distance, right? That was when, right? So d is this distance vector, and F was that force vector, right? But when you say force times distance, you mean the force and the distance are in the same direction. But when they're not in the same direction, it's just the component of F along D. right? The component of f along d times the length of d. It was f dot d, right? It's like force times distance, but it's not the ordinary times. It's the dot product times, right? If you remember that back from the first section, section 2, or chapter 2, section 2.3, when we covered dot product. Okay, so again, subdivide the interval from a to b into n subintervals of length delta t equal to b minus a over n. And let ty equal a plus I delta t. All right, so we've got our curve. So again, I'll draw stuff in 2 dimensions again. We've got our curve, traveling from here. So that's r of a. This is r of b, and we're going in that direction. R of t1, r of t2, r of t3, right? We've got all these curves, these points along the curve. Now, how did we represent the curve before? How did we approximate the curve, right? We used these line segments, which we could do here again to approximate the curve. Okay, intuitively that's the clearest thing, right? I mean, when delta t is really tiny, and you've got lots of these sampling points, right? Connecting these points via straight lines definitely gives you a nice approximation to the curve of C. Okay, but there's another way to do it, which isn't quite as intuitively clear, but it makes the calculation easier. So it's intuitively clear to approximate the curve using these line segments. But there's actually another way to do it. It's less intuitively clear, but it makes the calculations easier. Instead, you approximate with tangents to the curve. And the tangents are what? It's r prime. Which shouldn't come as too big a surprise because the length of the curve is given by the tangent function, r prime. So these curves, this is going to be r prime of a. And you don't use the whole curve. It's r prime of a scaled by delta t. R prime of t1 delta t, r prime of t2 delta t, r prime of t3 delta t, r prime of t4 delta t, and r prime t5 delta t. Right, the length of the curve, right, was equal to the integral from a to b of the length of r prime of t dt. Right, so the curve is approximated by r prime. So that's what we're going to do here. We're going to approximate the curve by, right, and this is the limit of the sum, right, of r prime of t dt. So length r prime of t dt, it approximates the curve. So instead of just using the lengths, we're going to use the vectors themselves to approximate the curve. So the work done along each small segment is approximately the dot product. So this is going to be segment 1, segment 2, segment 3, segment 4, segment 5, segment 6, so on and so forth. The work done by force field F, and in this case it's Fxy because we're working in 2 dimensions, along segment SI. So this is segment SI. Well, let's actually call this segment S0, S1, S2, S3, S4, S5. So the tangent vector r prime t I delta t, it approximates that little bit of the curve SI. Right? And as delta t gets really tiny, the approximation gets better and better. Like this is SI and this is the tangent vector. They become very close together. So the work done along segment SI is approximately F of R of T I dot, right, it's dot product, R prime T I delta T. It's just the force field F, dot product, the movement vector, the vector of movement from here to here, which approximates the movement from here to here. You can use the straight line movement from here to here as an approximation as well. Intuitively, it's more clear, but the calculation is much easier this way. And we've already seen that the tangent function does, in fact, estimate the curve. So the work done all along C, the total work done by force field F along C in its entirety is approximately the sum I equals 1 to n f of, little f, capital F of R of T I dot R prime T I delta T. Right, you just add up the work, approximate work done on each segment, and the approximation gets better as delta t goes to 0. In other words, as n goes to infinity. So the actual work done is, so this is the work done by F along C is equal to the limit as n goes to infinity, the sum I equals 1 to n, this thing right here, f of r t I dot r prime of t delta t. But this is equal to an integral because it's a function with respect to t. The dot product of two vector functions gives you a scalar function with regard to t. Ti, I guess here. So that's the integral from a to b of this vector function, this scalar function here, which is the dot product of capital F dot r prime of t dt. Again, we made no specific reference to r itself and how r represents c. We just said that r does represent c And so no matter how, no matter how you pick r, if you have two different versions of r representing the same c, the integral will come out to be the same, even though the integrals are different, just like with the scalar line integral. Again, if r1 of t and r2 of t both represent c, then the respective integrals line integrals are the same. Okay, so sometimes it's useful to refer to the integral without reference to r at all. So we refer to the integral without reference r as follows. So it's just the line integral over the directed curve c, f of x, y dot ds, or for a three-variable function, f x, y, z dot ds, like that. Okay, so the ds is like the r prime of t dt, and it's a dot product, not ordinary multiplication. Where when r of t for a less than or equal to t less than or equal to b represents c, then the line integral of c along c of f dot ds, so this is not even mentioning x, y, and z, just f dot ds, and that's just fine, nice compact notation, is equal to the integral from a to b of f of r of t dot r prime of t dt. So that's how we refer to and encode this line integral. Okay, so let's do some examples. Let's go back to that. Let's go back to that whirlpool example we had before. Let me do some copying and pasting. That whirlpool vector field, where did it go? There it is. Should we do that one? That one's going to be more difficult. So here's the picture of the vector field. So let's say that f is equal to minus y comma x, which was this guy here. All right, this vector field here, and let's take the path to be this parabolic path. So we'll say that's the point minus 2, 4, and this is the point 2, 4, and we're going in this direction. So that's the curve C. Say f is equal to this, and C is the parabolic curve shown. Okay, calculate the integral f dot ds. So again, nice compact notation. We don't even say fxy, right? So it's just f dot ds. All right. Well, you know, I didn't give you r. I didn't say what r is. We have to figure out what r should be. So, well, I mean, if that's the parabola, right? The parabola is y equals x squared. All right. Let's pick r of t to be equal to, well, x is equal to t, and then this is just, you know, this is just y equals f of x squared. So let x be t and y be f of t, which is t squared. For minus 2 less than or equal to t less than or equal to 2, right? From minus 2 to 2. Okay, so pick r of t to be equal to that. So r prime of t is what? Is just 1 comma 2t. Right, so now line integral over c of f dot ds is equal to, let's just write it out, integral from a to b of f of r of t dot r prime of t dt. So that's the integral from minus 2 to 2. Now what is f of r of t? All right, well, f is minus y comma x. R of t is x equal to t, y equal to t squared. Right? So f of r is equal to what? Minus y, and y is equal to t squared. So this is minus y, comma, x. Minus y, comma, x. So x is t. So this is minus y, comma, x. So that's f of r of t. It's the value of f along the points for r of t. So x and y are both expressed in terms of t. Dot r prime of t, which is 1, 2t dt. Right, so this is equal to the integral from minus 2 to 2. So now we evaluate the dot product. Minus t squared plus 2t squared dt. And comes out to be something not too difficult. Integral from minus 2 to 2, t squared. So this is equal to 1/3 t to the third from minus 2 to 2. So that's 8 plus 8. So 16 thirds. Okay, so the work done there is 16 thirds, you know, whatever units of work you're doing there, joules or Newton meters per second, or sorry, Newton meters, whatever the case might be. All right. Here's an alternative notation. Okay, an alternative notation. I don't like to use it, but you know, the book uses it and other people use it. Given a vector field fxy equal to p of xy, q of xy, right, and r of t equal to x of t comma y of t, right, the integral over c f dot ds is equal to the integral from a to b, whatever a and b are, right, p comma q, that's f. I'm not even going to put the xy, it's just p comma q, dot r prime is just going to be x prime of t, y prime of t dt. Oops. evaluate that dot product, it's equal to the integral from a to b, p times x prime of t. So let's put the x, no, let's not do that. X prime of t dt plus q times y prime of t dt. Right, which has this special notation the integral over c p x prime of t dt, just call it dx, plus, they might have it like this, wow, plus q y prime of t dt, just call it dy, right? Or integral over c p dx plus integral over c q dy, where integral over c p dx is equal to the integral from a to b, p x prime of t dt, and integral over c q is equal to the integral from a to b q, or dy, y prime of t dt. So sometimes folks will want to calculate this just on its own instead of calculating the whole thing. Sometimes it's meaningful to just calculate this one on its own, just the line integral in the x direction, so to speak, or the line integral in the y direction, so to speak. Okay, so the work done in the x direction plus the work done in the y direction. In for three-dimensional functions, the notation is sort of the same. Vector field f x y z equal to p x y z q x y z r x y z. We write same sort of thing, the line integral over c of, did I put the c underneath it? Yeah, I didn't put the little arrow on it. Bing, bing, bing. We put the little arrow on the c here because the direction matters. The integral over c of f dot ds is equal to, so integral over c p dx plus q dy plus r dz, right, where same meaning as before. P dx is that, q dy is this, and integral over c r dz is equal to the integral from a to b r z prime of t dt. Okay, so that's an alternative notation, and it is meaningful sometimes to calculate those three-line integrals separately. So work done in the x direction plus the work done in the y direction plus the work done in the z direction will be the total amount of work done altogether. All right, so that's the end of the lecture on section 6.2.